Okay, so in this small tutorial video, we're going to talk about the expression for the torsion pendulum, right? So for the torsion pendulum, we are assuming that this is like a rigid disc and which is attached to a wire, right? And then the wire will provide a kind of like a spring constant in our mass spring system. This is a disc which is changes the K, which is a constant for a spring, to a kappa, right? And that's a constant for our torsion pendulum. So we're going to draw that, and we can draw the disc like this. All right, so you have a disc which is attached to the center, and let's say this is the way it's going, right? It's going from here to here. So we can say that this is the angle theta, that it is maximum, doing a rotation. So that's a theta max, right? And that's about that it is going along that. So here the disk is rotating with the small angle theta, okay, and then it is released so that it's gonna go rotate. Of course, this wire is exerting a torque on it too, right? So here you have, we can write, if a disk is rotated a small angle, let's say theta, and released, right? So in our simple pendulum, what we do is we bring the pendulum or the bob on the one side and then let it go, so it goes back and forth. Here's the same thing. We're going to turn the disc with the angle theta and then released, so that it can provide a torsion pendulum with it too. So if a disc is rotated a small angle theta and released, the wire exerts the torque. The wire exerts torque. Now, what is the torque? Now, so in this case, we're going to have your torque as F, instead of F equals to Kx in the simple harmonic motion. Here, your torque tau would be negative kappa, which is like a small Greek letter we're going to use instead of a K, kappa theta. True? So we can say your kappa is nothing but the torsion constant. And of course, it is depending on the wire. It depends on the physical property of a wire. It depends on the physical property of a wire. Okay. So what else we can say? Well, see, this is torque tau. We can say torque tau equals to I alpha as our early definition. We can relate that with a kappa for the torsion pendulum constant and theta. What we can know for alpha, of course, is your alpha is d squared theta over dt squared, the second order differential equation for the angular displacement, and that can be related as kappa theta. So I can have you now for the torsion pendulum, the equation for the second order differential equation as negative kappa theta over I. Here we go, right? So now what else? This is same as a periodic simple harmonic motion, right? This is the similar as a simple harmonic motion, because in simple harmonic motion, if you remember, we had d square x dt square, and that's equals to negative omega square x. This is the same thing. So we can relate this and rewrite the whole equation for the period again. So if you rewrite this for the period for the torsion pendulum, it will come out as I over kappa, right? So this would be the period equation for your torsion pendulum. I know there are 4 different period equations in this unit, and I think this is the good time for list them all and have it for you. Now, the one exception is that we do not need to do a small angle approximation as we did always for simple pendulum. The reason is because the simple pendulum, we have a proportionality with the sine theta for the restoring torque, restoring force rather. And here in a torsion pendulum, the torque is your restoring torque right here. Your restoring torque is proportional to only theta. Restoring torque for a pendulum is proportional to theta, not proportional to sine theta. That's the basic difference you have between simple pendulum and torsion pendulum. So 4 types of things we have learned for the pendulum. The last one is the torsion pendulum, right? So for the torsion pendulum, we can have a t equals to 2 pi square root I over kappa, which is a torsion constant. For a physical pendulum, right? For a physical pendulum, you can have your t equals to 2 pi square root I over mgr. For your simple pendulum, right? For your simple pendulum, you can have your t equals to 2 pi square root L over G. And for your mass spring system, your t is 2 pi square root m over k. Right? So these are all different period equation you can have for the pendulum. Thank you. I hope this helps.